All right, so this one does get a little bit dicier. We need to start with this Euler identity version of cosine, which basically tells us that it's equal to e to the j omega t plus e to the minus j omega t all over 2. I left a link to a YouTube video that explains how this comes to be from Euler's identity. You can also see it in the textbook, table 7-2 of the Eulaby textbook. Goes over representing sine and cosine in terms of complex exponentials. This is essential to complex numbers, and so in order to solve this, we need to convert cosine over to this form. And so let's just take the Laplace transform of f2 of t. That's what we want to do here, is find the Laplace transform, which we know in this case is going to give us some new function of s. And that's going to be equal to the integral, of course, from 0 to infinity of f2 of t, which in this case is going to be e to the j omega t, e to the minus j omega t, divided by 2 times e to the minus s t dt. So right off the bat, we can split this into two integrals and we can pull a 1/2 out. So let's just pull the 1/2 out, split it into two integrals. So we'll integrate from 0 to infinity of e to the j omega t times e to the minus st dt, plus the integral from 0 to infinity e to the minus j omega t e to the minus st dt. All right, and so that's the integral that we're going to need to solve. We can, of course, rewrite this using exponential rules as e to the j omega minus s t plus e to the minus j omega plus s times t dt. This doesn't look great. Oops. All right. And then from here, we can just say that that integral is basically going to be e to the j omega minus s t divided by j omega minus s from 0 to infinity. And then we can also say that this one is going to be e to the minus j omega plus s t divided by minus j omega plus s from 0 to infinity. All right, and so if we go through plugging in infinity and 0 to t for these two integrals, the first one, we basically just get 0 over j omega minus s minus 1 over j omega minus s plus another 0 over negative j omega plus s. And then the last one is just going to be negative, so I'm going to get a positive, so it'll be a plus 1 over negative j omega plus s. And so ultimately, I get that this is equal to 1/2 times, let me see, did I do something wrong? I think I have a double negative here somewhere. So it's negative, yeah, this is supposed to become positive. Okay, so this becomes positive, and then I've got 1 over basically s plus j omega minus 1 over s negative s plus j omega. And we can rewrite this as we have to basically multiply both of these by their complex conjugates. And so we get a half, 1 over s plus j omega times s minus j omega over s minus j omega for that first term, minus 1 over negative s plus j omega times negative s minus j omega over negative s minus j omega. Then we get, let's see, so on the bottom here, that's going to give me s minus j omega in the numerator, And then in the denominator, I get an s squared. Of course, these two terms get squared, and then the s times negative j omega and the s times positive j omega cancel. So I just get s squared plus omega squared. And then I get this minus, let's see here, it's going to be negative s minus j omega on the numerator divided by, and then down here again I'm going to get s squared plus omega squared. Okay. And so my s and my minus negative s becomes a 2s, and my negative j omega and my negative j omega cancel here. So I'm just left with 1/2 times 2s over s squared plus omega squared, which ultimately, oh, I left a ton of room here. Okay, so ultimately the 1/2 and the 2 cancel, and I get that the Laplace transform of my f2 of t is equal to s over s squared plus omega squared. Okay, and so that is the Laplace transform of this cosine signal, cosine of omega t. And yeah, the math gets really dicey with these Laplace transforms, so I just wanted to show a couple of examples, show you kind of how the process goes. And you can compare this against a Laplace transform table, and you will see that this is the case. But when, like I said, we're going to try to hopefully get to the point where we're just using the Laplace transform table so we don't have to do this math every time, okay? So I'm going to end this video here, and we'll see you guys in the next video.